Hello, everybody. Welcome back. Today we're going to be looking at Unit 6.7, which is all about bond enthalpies. Remember, enthalpy is just a fancy word for energy, so bond energies. So let's get started. So before we get to any of the calculations or even definitions, it is important, guys, that you understand what a chemical bond is. A chemical bond is not something that you can, physically touch. A chemical bond is nothing more than a force, that's existing between groups of atoms and making them function as a unit. So it's really important that you understand that a bond isn't something physical that we can touch. It's nothing more than a force. So the concept that's being taught here in Unit 6.7 is bond energy or bond enthalpy, same thing. Okay, and that is defined as the energy that is stored within a chemical bond. And depending on the number, the number for a particular bond, its bond energy, gives us information about the strength of that bond. And I want to just show you an example here. If you're comparing, for example, a carbon-to-carbon single bond, a carbon-to-carbon double bond, a carbon-to-carbon triple bond, notice that the bond energies are increasing, and that should make sense to you, okay? A single bond versus a triple bond has much more energy stored in it than a single bond does. So when you see bond energies that are on the higher end, that's indicating a stronger force of attraction between those bonds. And let's kind of tie this to some concepts that we've talked about in previous units. When you break a bond, or a bond is broken, that requires energy. That's an endothermic process. Remember, it takes to break. And conversely, if a bond is created, a bond is formed, it's almost like the bond releases a sigh of relief, like it releases energy. That is an exothermic process, free to form. Energy is freed when things are formed. So let's just make sure we understand this concept. We saw on the previous slide that a carbon-to-carbon single bond has a bond energy of 347 kilojoules per mole. So what does that mean? That means that it would require 347 kilojoules to break not just one bond, but a mole, 6.02 times 10 to the 23rd, carbon-to-carbon single bonds. But the key here is the word required. Whereas 347 kilojoules of energy will be released when 6.02 times 10 to the 23rd carbon-to-carbon single bonds are formed. So you can look at that number in two different ways. Are we breaking the bond, or is the bond being formed? Now, we have seen thus far, multiple ways to calculate the delta H of a reaction. One in particular being that you can look at it from a reaction profile, products minus reactants. And I'm going to show you another way to calculate the delta H, the change in heat, the change in enthalpy for a chemical reaction. And that is using bond energies that are involved in that chemical reaction. That symbol that you're seeing there, sigma, that means the sum of. That capital D is just a variable that is standing for bond energies. So we can calculate the delta H of a reaction by summing up all of the bond energies of all the bonds that are being broken minus summing up all the bond energies of the bonds that are being formed. Okay, the first part, those are endothermic. The second part, those are exothermic. Now, some people like to, instead of making this formula bonds broken minus bonds formed, some people prefer to write it out as an addition instead of a subtraction, but making sure that you know that all of those bond energies should be negative because it's energy being released. I personally prefer to just keep all of the bond energies positive and just remember bonds broken minus bonds formed. But if you prefer to do everything as adding all together, you can certainly do that. Just make sure that you make all of those numbers negative. Okay, it's the same mathematical process. You do not have to memorize any bond energies. In an AP question, they would always be given to you. If you look in your textbooks, you'll also find a huge chart that lists all the different bond energies that are typically used in calculations. So nothing to memorize. So let's look at a sample question. It says, using the bond energies listed, calculate delta H for this reaction, okay? And this is a nice simple one, and the AP exam typically doesn't give really, really complex reactions. So here's what I'm going to do. I'm going to do this one with you, and then I'm going to have you do one as practice on your own. Remember the formula. Delta H is equal to, actually, let me put it down here. Right here. Delta H equals, I'm going to put a big set of brackets there. Bonds broken. Well, where are the bonds that are being broken? They're on the reactant side. Okay, everything on the reactant side of a reaction, those are where the bonds are being broken. Those are the first ones I'm going to deal with. So what's being broken? The first thing to be broken is a nitrogen to nitrogen triple bond, which has a bond energy of 941. That's not the only thing that's going to be broken. I'm also going to be breaking not one, not two, but 3 hydrogen to hydrogen bonds, because that's what's right here in this second reactant. It's a hydrogen to hydrogen bond, and there are 3 of them. So I'm going to do this. 3 times 432, and then I'm going to close the bracket, meaning that is all of the bonds that are being broken. Bonds broken minus bonds formed. Where do I find that? That's going to be on the product side. Let me say that again. Bonds formed are always on the product side. And guys, remember what ammonia's structure looks like. Okay. One ammonia molecule has 3 N to H single bonds times 2. So how many total N to H single bonds are there? There are 6 of them. So I'm going to multiply 6 times 391. And then I'm ready to do my calculation here. Let me just put this in my calculator. Let's see what we get. Okay. I get negative 109 kilojoules. Okay, and if you look at the final answer, remember guys, this is the delta H for this whole chemical reaction. This is yet another way to find the delta H, the change in enthalpy for this reaction. And look at my answer, it comes out negative. What type of chemical reactions have negative delta H values? Exothermic. This reaction overall, must be exothermic. Let's think about, would that, if that were going on inside a beaker and you were holding the beaker, would it feel hot or cold to your hands? It would feel hot. Remember, exothermic means heat is leaving the system. Where is it going? To the surroundings. You are part of the surroundings. Okay, so that's how you do a bond energy calculation. And I would like for you guys to try this one on your own. You are given a reaction. You're given a table of bond energies, and they want you to see which energy profile matches up with the delta H that you could calculate from these bond energies. So pause your video and see how you do with it. All right. So we've got our balanced chemical equation, and it says, based on the bond energies shown in the table below, which of the following diagrams best represents the energy change, or the change in energy as the reaction represented below proceeds? So this was meant to be done without a calculator, which I think you can do. It's a little bit of number crunching, okay? But when I do bonds broken minus bonds formed, I end up with a number of negative 190. Even if you were pretty close, even if you realized that it was somewhere near negative 200, you could still get the answer. Okay, now, the answer is negative. Remember what that means. That means exothermic. That means I can eliminate answer choices C and D right away because both of those have the general shape of an endothermic curve. So those are out. A and B are both showing an exothermic curve, and the answer is just which one is showing that appropriate difference, that overall delta H, and that is not letter B. So answer choice A is my answer. So that not only required you to do a bond energy calculation, but also to tie it in with some things we've talked about in previous units. So that's it for bond enthalpies, and I hope you have learned a little something today, and I look forward to seeing you next time.